Hello and welcome to the lecture series on power semiconductor controllers. In today's lecture would be starting the basics about load resonant converters. Load resonant converters are basically those type of resonant converters which utilizes some type of tank circuit with the load and thereby employing zero voltage and zero current switching. But before going into the resonant load converters, first let us look into two basic type of circuits which involve a DC power supply and two passive components, one being inductor and the second being the capacitor. This is basically an undamped series resonant circuit. Similarly, we will be looking into undamped parallel resonant circuit, and we will also be looking into one more type of circuit which is basically the series resonant circuit with a capacitor in parallel with the load. So, we will be utilizing the result obtained in these basic type of circuits in analyzing a load resonant converter in the various types of load resonant converters, and basically we will be studying about series and parallel load resonant converters. So, let us start. So, let us try to analyze this simple circuit. We have got a DC power supply VD and an inductor LR and a capacitor CR. ILR is the current flowing through the inductor. Let us try to find out the expression for the inductor current and the voltage that would be appearing across the capacitor. Let me call it VCR. So, for that I have to write down the differential equation governing this circuit, and I can write it down by applying KVL in the equation. So, let me write it down here. So, LR di LR by dt plus VCR will be equal to VD. Okay. So, if I try to apply the KVL in this circuit. Okay. Moreover, we also know the relation between the current flowing in the capacitor and the voltage appearing across the capacitor, and that is given by CR dVC by dt, let me call it dVCR by dt, is equal to ICR. And since this is in this circuit LR and CR are in series, so basically the current ICR will also be equal to the current ILR. Now, if I try to differentiate the first equation one more time, so what I get? So, LR d2 ILR by dt2 plus dVCR by dt is equal to 0, and from here I can write down dVCR by dt in terms of ILR. So, basically I will get LR d2 ILR by dt2 plus, in place of this I can write ILR by CR, and this is equal to 0. Now, this is a simple second order linear differential equation, and we can solve it quite easily applying some analytical mathematics, and right now I won't be going into that. I would just be writing the result for it. So, the current ILR as a function of time t would be given by IL naught cos of omega naught t minus t naught plus Vd minus Vco upon Z naught sine of omega naught t minus t naught, where t naught is the initial position where we are making the measurement, and t is any time. IL naught is the initial inductor current, while Vc naught is the initial capacitor voltage. Okay, and omega naught and z naught are well known. Omega naught is basically given by 1 over root over LR CR, and z naught is root over LR upon CR. Fine. Now let me write down the equation for Vc also. So Vc as a CR as a function of t can be written as, we can obtain VCR. Once we have obtained this ILR, we can easily obtain VCR by differentiating it once using the relation I had written here. Okay. So VCRT is equal to VD minus VC0 cos of omega naught t minus t naught plus z naught IL naught sine of omega naught t minus t naught. So this is the expression for the voltage that will be appearing across the capacitor. I had tried to plot these two variation of current and voltage here, and on the x axis we have got omega t, which is basically an angle, and I have assumed that initial current through the inductor is 0.5 and the voltage across the capacitor is 0.75. This is a normalized value. This is the normalized value. Basically we can write this expression in normalized form by dividing the current by a base value of current, and that is given by Vd by Z naught, and we can also divide the base VCR by the base value voltage, V base equals to Vd. So if I divide these two, VCR by V base and ILR by I base, I will get normalized values of inductor current and capacitor voltage, and I had tried to plot it here. So you can see a clear phase lag between the voltage that will be appearing across the capacitor and the current flowing in the inductor. Okay. So this is these two expressions are quite important, and when we would be trying to discuss series and resonant series and parallel resonant load resonant converters, we would be invoking these two relations. Okay. For series we will be invoking, for parallel again I have to derive the relations for this. Okay. So let us now try to derive the relation for VCR and LCR when I have got a capacitor in parallel with the load. Okay. So I have drawn here an undamped series resonant circuit with capacitor in parallel with the load. Load here has been shown as current sink, which normally we do show if there is an inductor at the load side. Okay. So let us try to analyze it, although I do have written all the equations governing this circuit. So for this circuit, VCR, the voltage that will be appearing across the capacitor, VCR, this is plus, this is minus, can be written as Vd minus LR dir by dt. So basically I have applied KVL in this loop. Okay. Moreover, if I try to apply KCL at this node, then the current that is coming at this node is ILR, and that is going out of this node is ICR and I naught. So basically ILR minus IC is I naught. Then what we are doing, we are basically differentiating this equation 1 once, so, and multiplying it both sides by CR. So, if you differentiate this dVCR by dt, and Vd is constant, so 0, minus of Lr d2 ILR by dt, and multiplying both sides by CR, you get this. Then from this equation, let me call it equation 3, from equation 3 and equation 2, I can write, I can obtain this expression. Okay. Okay. Then this is again second order differential equation, and I can solve this equation, and I will get the expression for ILR and VCR, which I have written it here, I naught plus I naught IL naught minus I naught, and this similarly for VCR. So, you will see some similarity with the expression that we derived when there was no parallel capacitor load in a undamped series resonant circuit and this circuit. So, the difference is in the previous circuit there was only IL naught, there was no I naught. Okay. So, if you make I naught equal to 0, you will arrive at the previous circuit. So, that means this is a more generalized form of the circuit wherein there is no I naught. In the next expression also, if you put I naught equal to 0, you will arrive at the same expression for the previous circuit. Now, let us see an undamped resonant parallel circuit. Okay. So, let us take the case of undamped parallel resonant circuit. I have drawn the circuit here. In this circuit, this the source is a current source, okay, and inductor and the capacitor, they are basically in parallel. So, the equations that would be governing this circuit would be, let us try to apply KCL here. So, if I apply KCL here, this equation would result ILR plus ICR would be given by ID, while ICR is given by this expression. Moreover, since the capacitor voltage and the inductor, the capacitor and the inductor are in parallel, that's why so the voltage that would be appearing across the two would be same. So, VCR equal to VLR, and VLR is nothing but LR DILR by dt. Now, combining this and this equation 1 and 2, we will again get a second order differential equation. If I solve it, then I can get the expression for ILT and ILRT and VCRT. That would be given by the expression that I have written here. Okay. So, these are some of the expressions related to some basic resonant circuits, and we would be utilizing these results when we discuss the load resonant converters. So, it is important to note these two the equations that we have developed so far. Okay, thank you.